Hello everyone, I'm Norman Wildberger from the University of New South Wales, and with me is Daniel Mansfield.
Hello.
So today we want to continue our discussion of the fascinating OB, or Old Babylonian mathematical culture, and we want to head towards geometry and how they thought about geometrical things. And it's interesting that their point of view was not always aligned with ours.
In particular, their geometry seems to be exact, whereas our geometry is almost always approximate.
Yeah. So maybe we can start with just a general overview of the kinds of places or topics that would have been important for them. So they lived, as we've talked already, in this fertile crescent region between the Tigris and the Euphrates rivers, and these rivers are subject to floods quite regularly, and the floods are quite irregular. And so it often would be the case that fields would be flooded, and then surveyors would have to sort of reestablish the boundaries and the markings for these things. And that certainly is, they share that with the Egyptians, that there's a need for geometry for surveyors.
And we have lots of examples of surveyors' texts where they would perform exercises involving, in particular, the areas of fields.
Yeah, so the areas would have been important because the area of a field determines how much grain we can expect, and so the tax collectors would be interested in determining that, to assess taxes and such. So calculations of areas was another common kind of preoccupation that they had.
Yeah. But they were also avid canal builders. In between these two rivers, they also had many canals which would irrigate the land and bring crops, and people could build cities dependent upon these canals. So we have many exercises concerning the canal construction, how much volume of dirt would have to be excavated from these canals, how much silver you'd have to pay the hired people to dig these canals. They're quite sophisticated, actually. Some of them mathematically acknowledge that the dirt at the bottom of the canal is actually harder to extract, and therefore you should pay your workers more for extracting that.
We'll even have an example of such a canal problem later on in this video. And of course, building of temples and ziggurats, so most of that stuff is no longer with us, with the notable exception of the ziggurat of Ur, which is a really remarkable building which is still around. But otherwise, there isn't that much left. But nevertheless, we're pretty confident that they would have built actually quite elaborate temples, beautiful temples. They just built out of clay and mud, and so it didn't last quite as long. But still, the usual challenges of building would have been there for them.
Certainly, and we have many examples of construction of walls, again out of mud, and all the mathematical exercises associated to the volumes and areas and number of bricks you have to build a house. And these are very contrived examples to really emphasize the mathematics behind these things. There's examples of you have this much bricks, how much house can you build? And you have this much house, how much bricks do you need? Examples such as that.
Yeah. And something that's really only become apparent perhaps in the last few decades with the work of Jens Hoyrup is the close connection that geometrical thinking had with their algebraic or, say, arithmetical work. So especially with regard to quadratic problems, and we'll see also an example of that later on in this video.
But that's a relatively new development. Previously, people have thought that what we see on these tablets is all they did, and really the remarkable insight that came along with Hoyrup was that this is only a fraction of what they did, and really describes a process that was performed elsewhere, a geometric process that was perhaps drawn in sand, but certainly only a fraction of what was actually done. The old Babylonians lived over 3,700 years ago, and as you can imagine, a lot has changed since then. The Babylonians thought about shapes such as right triangles and circles in a very different way to us. They thought about a right triangle as half of a rectangle. So the measurements of a right triangle are not the opposite, adjacent, and hypotenuse, but the short side and long side of a rectangle, as well as the diagonal of a rectangle. They also thought about a circle differently to us. If you ask any mathematics student what the area of a circle is, they tell you that it's pi r squared. But if you ask a Babylonian what was the area of a circle, they tell you that it was the circumference squared divided by 12. And why would they think that? Well, the circumference is something they could measure. If you have a circle, they could actually measure this. It's much harder to get to the circle and talk about its radius. So this is just a different way of thinking about a circle. And of course, this is equivalent to pi r squared. If c is just 2 pi r, then this ends up being pi r squared, where they've used the approximation of pi being equal to 3, which is not as good as our approximations to pi, but it's actually a pretty good approximation, and it's a regular approximation. So they could divide by 3. So there's a lot of good things about using the approximation pi equals 3.
Some of the ancient Mesopotamian approach to geometry was actually shared by the Egyptian culture. And it's interesting to especially think about a particular quantity that actually plays a big role in our story, which is describing the inclination of a sloping line or a ramp or maybe the side of a pyramid. So this was a measurement that both the Egyptians and the Old Babylonians thought a lot about and used. And it's a little bit outside our familiar sort of thinking. So they measured, the Egyptians had this notion of seked. And the seked was defined as a measurement of the inclination of a sloping line. But it was run over rise. So undergraduates learn about rise over run being the slope. So for the Egyptians, it was the reciprocal run over rise. So you took the run, in this case, and you divided it by the rise to get the quantity of interest. And often this is normalized so that the rise is equal to 1. So the Egyptians referred to a seked of so much per unit cubit. So in Egyptian times, standard measurement was a cubit, which was roughly the length from an elbow to the tip of the fingers. And that cubit was then further subdivided into what are called palms, which are basically 4 fingers. And there are 7 palms in the royal cubit. So the Egyptians measured, for example, the sides of their pyramids using this measurement. And this was very important because they were avid pyramid builders. And so to maintain consistency, first of all, within a given construction, you have to make sure that the guys building this side of the pyramid and the guys building this side of the pyramid are kind of aligned so that when you get to the top, everything matches up. So the large-scale integrity, the long-term integrity of these pyramids really depended on very accurate construction. And so for that, the Egyptians had a very clear idea that, in order to go up 1 cubit, you needed to go a certain amount over. So for example, the Meidum pyramid built by Sneferu, which was one of the earliest pyramids, had a seked of 5 palms and 2 fingers. What does that mean? It means that the base is 5 palms, that's 5 of these ones, and 2 fingers, while the rise was the standard 1 cubit, or 7 palms. So in terms of ratios, there would be 14 this way and 11 this way. That's what we would say is the slope, okay? And we could also maybe use angles, refer to the angular measurement, but that would have been very alien to both the Egyptians and the Old Babylonians. Now that's I think about 52 degrees, slightly less than 52 degrees. And this was such an important measurement that a lot of other subsequent pyramids also adopted exactly that same seked. So for example, Khufu's pyramid, the Great Pyramid, which is the most famous, also has exactly the same seked of 5 palms and 2 fingers. While his son Khafra, the middle pyramid, it has a seked of 5 palms and 1 finger. While his son Menkaura had a pyramid that went back to the older version of 5 palms and 2 fingers. And there were, of course, dozens of pyramids built over the millennia, and we can trace out that they really liked certain kinds of sekeds more than others. So aside from these ones, sekeds of 5 and 4 and sometimes 6 are also seen. And so there's often some repetition and kind of uniformity in the use of these things. So it's very clear that they had a very, very determined measurement that was very important to them, that they studied very intensely. And making this just the right inclination was critical for them to ensure the stability of their pyramids.
So the ancient Egyptian notion of seked actually also appears in contemporary Babylonian culture. But they called it the ukulu. They would talk about how much a triangle eats per unit depth. And in fact, they would talk about how much fruit it eats per unit depth. So this triangle over here, in order to go down 1 unit, you would have, how much would you have to go across? And of course, you'd have to go across B divided by L in this particular triangle. And that's how much the triangle would eat per unit depth. Interestingly, for the Babylonians, this same notion of how much it eats per unit depth also applies to a trapezoid. And this is a very important shape for the ancient Babylonians. They would build walls out of mud, and of course the slope of the walls would form a trapezoid. Or when they dug a canal, the sloping sides of a canal with a flat base would also form a trapezoid. So this is a very fundamental object for them. And this notion of its steepness is exactly the same. They would talk about the indanum of a trapezoid being the difference between these two things divided by the height.
All right, so here's an example of a reasonably well-known tablet and a problem called a Little Canal problem, which talks about a canal that is being built. So here is the transcription of the actual problem. A little canal. 5 us is the length, 3 cus the upper width, 2 cus the lower width, 2 cus its depth, 10 gin is the volume, the assignment. What is the inclination per 1 cus depth? And then the problem gives the answer. 1/2 cus is the inclination.
And in the words, it's actually asking about how much this trapezoid eats. So we're already familiar with how much a triangle would eat. It's the same kind of terminology for how much does this profile eat per unit depth. What's not given in the question is what particular profile it has. So you can imagine this as having, say, a vertical side here, or you can imagine it as some kind of arbitrarily sloped trapezoid. It actually doesn't matter. In fact, both objects have the same inclination.
In terms of the indanum
Yes.
concept, because that was a concept that was valid to them. So we have a sort of a different possibilities about how to interpret what the question is talking about, but there's actually at least 2 different ways that both really revolve around this amount eating per unit depth.
But what is clear is how they thought about sloping sides. They thought about it as an amount per unit depth. This is a very different kind of geometric problem. In fact, it wasn't at first realized that this is a geometric problem until fairly recently. The text of this tablet reads, I added the area and side of my square and got 0.45. Now, initially this doesn't make a lot of sense. If you add an area to a length, that doesn't make any sense. Until you realize what they're actually talking about is a geometric construction. And this is really due to Heurup, who realized, hang on a second, this isn't just numbers being shunted around. They're talking about a geometric construction here. And it's actually the geometric construction of completing the square.
Yeah. And I remind you that usually historians attribute the completing the square procedure and the corresponding quadratic formula to the Arab mathematician Al-Khwarizmi, in maybe 800 or 900 AD. So this is essentially 3,000 years before that, and it's pretty clear that they really understood the quadratic formula and the completing the square procedure, as we're going to see here.
Yeah, and they understood it geometrically. So let's talk about this, but we'll have a picture in our minds as we read through this. So we have an area and the side of a square, and it produces this. So we can imagine a shape of area 45. We'll write it as 0.45.
Maybe I could just say, yeah. So here's the square that we're talking about. Okay, so that has some unknown side, and the side of the square is represented by this rectangle, which we are assuming has a length there of 1. So that means its area is now the same as that, which is the side of the square. So with this is sort of a way of taking this one-dimensional quantity of the side and creating a two-dimensional object out of it by just multiplying it by 1, essentially.
And what they do is they take this object which they've constructed and break it in half. So they take this one and they put it down here to make this L-shaped object, this L-shaped object here. And then they have to fill this in to complete the square. So you take the one, break it in half to obtain this length, and of course the missing bit is a square of sides 30. So to obtain that area, or to fill in the missing area, you have to multiply 30 by 30 and add it to the 45. And then what you have is a square of area 1.
And of course the 30 is really 30 or 1/2, so in the context of what we're doing, we would rather write 1/2 there, but they didn't write fractions, so they would have written 30.
Now to obtain this side length, all you have to do is take the square root of 1, which is conveniently 1. And these questions are nicely constructed, so when you end up taking a square root, it's actually an easy exercise for you to do. Either it's 1 or it's something where you just look up your square root table and read it off. So here's a very easy square root for us to do. 1 is the square root, and now we're interested in this side, so we just subtract the 30 to get to this side, and the answer is 30. Hence the original square had side length 30.
Yeah. And now this procedure also illustrates their general approach to trying to explain stuff. So they didn't have algebra, they didn't have variables like we do, they couldn't write a formula. But what they could do is they could write down the steps that you employ. But what numbers are they going to use? They can't say, well, let x be this and y be that. They just employed the simplest kinds of numbers that they could, so that everybody could follow what's going on. That's why these numbers are so simple. It's not as if they're particularly interested in solving this particular problem. What they're interested in is laying out the procedure so that somebody else could come along with a different problem and basically substitute, these other numbers for these ones and still come up with an answer.
And you can see quite clearly there is an algorithm here. They've got 1, and they're taking explicitly the square root of 1. Would we bother to do that? I don't know. When your answer is 1, you just say, oh, it's 1. But they're explicitly demonstrating the method of completing the square here.
Yeah. And maybe we could also point out that 2,000 years later, when or maybe almost 2,000 years later, when Euclid came along and wrote the Elements, so he also has a very geometrical approach to algebraic problems involving rectangles and moving things around, and so we can sort of see the origins of that kind of thinking in this much earlier time. So I guess now we have had a little bit of experience with OB arithmetic and with OB geometry. So in our next video, we can look forward to actually sort of addressing the main point which we're interested in telling you about.
Yes, which is about Plimpton 322,
Yes.
which we can now hope to understand given we have the required background in Old Babylonian thinking.
Yes, so we hope that you'll all join us for that. I'm Norman Wahlberger.
I'm Daniel Mansfield.
See you next time.